Welcome to the Phenomenological Alliance channel. In this video, we will discuss the next question that phenomenology problematizes in the field of natural sciences, namely the issue of experimental suggestiveness.
Today, it is considered that the universal law of gravitation, mathematically formulated by Sir Isaac Newton, represents a fundamental interaction causing mutual attraction between all material objects. In mainstream physics, various pieces of evidence supporting the existence of gravitational interaction are cited, including the occurrence of tides, the rotation of planets, and the Cavendish experiment. In his book Mathematical Principles of Natural Philosophy, Newton asserted that one of the most apparent pieces of evidence for the existence of gravitational force is the occurrence of tides. The mass of water in the ocean is periodically attracted by the gravitational force of the Moon, resulting in the rise of the ocean water level. The description of the planet's orbit around the Sun is based on the gravitational model. The combined masses of the Sun and the Earth create the gravitational pull within the Sun-Earth system, resulting in the elliptical orbit of the Earth around the Sun. When two heavy lead balls are positioned near a torsional pendulum, the pendulum undergoes a change in its oscillation period over time. This happens due to the gravitational interaction between the lead balls and the torsional pendulum, resulting in a modification of the oscillation period.
When the problem of balance is included in the interpretation of tides, one can notice that the balance point between the gravity of the Earth and the Moon is more than 300,000 kilometers from the Earth. The most basic calculation involves balancing the gravitational forces of the Earth and the Moon. A more complex calculation is conducted based on Lagrange's assumptions, yet it still reveals that the equilibrium point is well beyond the Earth's sphere, since the Earth is about 81 times more massive than the Moon. The Moon's gravitational force alone may not be enough to displace the water mass. Closer to the Earth's gravitational force is stronger than that of the Moon, potentially counteracting the influence of the Moon's gravity. Also, there are other significant problems in the interpretation of tides through the gravity model. When examining the stability of the Earth-Moon system, one notices that the model of gravitational interaction lacks a satisfactory answer to the question of the solar system's stability. The calculation indicates that the Sun's gravitational pull on the Moon is approximately twice as strong as the Earth's gravitational pull on the Moon. Thus, we can justifiably ask, why doesn't Moon get pulled into a closer orbit to the Sun, as observed with artificial satellites in gravitational slingshot maneuvers? Nevertheless, adhering to the conviction that gravitational attraction causes tides and overlooking the problem of the solar system stability, which Newton was fully aware of, in 1797, Cavendish conducted an experiment demonstrating that the attractive force between masses can alter the oscillation of a torsion pendulum. Only 50 years later, Leon Foucault demonstrated that the oscillating pendulum deviates from the given path due to the motion of the Earth. The pendulum behaves like a gyroscope, always directing toward the balance point. In the Cavendish experiment, the presence of lead balls creates an illusion that the deviation occurs due to attraction between masses rather than the Earth's rotation. In the phenomenological approach, The concept of an attractive pulling force between matter poses a problem, as it isn't directly observable phenomena, but instead the concept emerged from calculation. On the other hand, the fundamental premise of the gravity model, namely that the stone attracts another stone, is entirely counterintuitive.
Today, we often talk about optical or other perceptual illusions when a person misinterprets what he or she perceives. These stances highlight the opinion that human perception is inherently subjective and is not a valid source of information for objective scientific conclusions. The real truth, however, is that the senses inform, the senses do not interpret. Interpretations belong to the area of thinking, and thinking is subject to conviction, which can be confirmed by experiments designed to justify initial convictions. Hence, in phenomenology, deductive or inductive logical reasoning is assigned secondary significance. Both approaches involve hypotheses that may or may not be correct. In phenomenology, the primary focus of research lies in the description of phenomena and an attempt to intuitively grasp their essence. Anything that appears counterintuitive is scrutinized with heightened attention.
In modern astrophysics, the explanation of the universe relies on two key concepts: gravitational interaction and the speed of light. And yet, it's far from the truth that there are no inconsistencies in the gravitational model. Let's explore whether there are inconsistencies in another key concept of modern astrophysics, namely in the concept of the speed of light.